Hello, everybody. Bom dia, boa tarde. Sorry. Good morning, good afternoon, good evening. Да, про me? Can you hear me?
Yeah, it's perfect.
Okay.
Yes, it's very good.
So, before to start seminar for today, I just want to make some deviation. Our seminar is called LieJor seminar. Lie and Jordan algebras means Lie and Jordan algebras. And we have the same series of conferences and Lie and Jordan algebras, their representations and so on. And when we speak on Lie and Jordan algebras, there is one name which associated with Lie and Jordan algebras maybe more than any other person, at least in our seminar. I mean, Efim Zelmanov. He's a real Lee Jordan person. He was created a structure theory of infinite dimensional Jordan algebras, and he solved several famous problems in Lie algebras. So he's really the most famous Lee Jordan person. A couple of days on, he also from the beginning supported and organized our conference in Lie Jordan algebras, regularly participated in all these seminars. And a couple of days before, he completed 65 years. It's just a remarkable date. So let's congratulate him with his anniversary and wish him health, happiness, and many more beautiful theorems. Happy birthday, Efim. A scientific brother of Efim from their scientific childhood in Novosibirsk, Professor Alexander Grishkov, want to say some words. Please, Sasha.
Sasha, turn on your microphone.
Sasha?
Excuse me. Excuse me. I forget to ask. Dear Fima, from the name of all seminar participants and me, I wish a happy birthday. We wish you happiness and health. Also, I want to say a few words about Jubilee. I am one of those men who knew Efim from the time of his scientific youth, when he was a graduate and then upper graduate student. Furthermore, I was lucky to see his everyday work and his lifestyle. Because of my life situation, he invited me to live a while in his apartment. In autumn of 1980, I moved to his place as an elder colleague, as I already had my PhD, but Efim not yet. But few months after, in November of 1980, I knew I was living in an apartment of great mathematician and man. I know Fima loves to cite Winston Churchill, so I'm going to do the same. When Sir Winston has been asked, what is the great man's major trait? He answered, responsibility. I did not know this story in that distant 80s years, but I was impressed of those traits, responsibility of young man Efim Zelmanov. I saw it when Efim has proved a beautiful theorem, but has been waiting for publishing it because of another mathematician who worked on the particular case of the same problem. Fima knew how important it is to publish his result first for this mathematician, and he was waiting. This ability to take care of the people around Fima has retained to this day. Happy birthday, Fima.
Okay, thank you, Sasha. So, happy birthday, Fima, once more. Okay, and now we return to our schedule. And Today we have as our guest, Professor Reimundo Heluani from IMPA. Reimundo,
I'm here.
so please, well, I don't know where is it. Can you say a talk? It's the title of your talk is.
I think. Let me just check that you guys. Oh no! Now I'm presenting something that I.
Okay.
I was supposed to present just a window. So thank you very much for the invitation, in particular in this very special day. Congratulations and happy birthday, Efim. It's an honor to give this talk during your birthday. Okay, so what I'll be talking about today, there are some handouts of these slides. My slides typically don't have any information, but they're very short. But in case you missed one of them, there's some handouts in this webpage, and you can have them there so that I don't need to go back and forth on the slides. What I'll talk about today is a very short paper that we posted a couple of months ago, joined with George Andrews and Jethro Van Ekeren here at UFI. And it's a very, in some sense, very simple result. It doesn't take long to read the paper nor to understand it. It's a very straightforward result. But I'm very surprised that this wasn't known somehow. And in particular, it's because the result is kind of ugly. And you're going to see it because in the fourth slide, I'm going to state the theorem, and then I'm just going to spend the rest of the talk saying some very basic stuff, and then finally the proof of that theorem. So today's talk is going to be about this Lie algebra here, the Virasoro Lie algebra. Hopefully you're seeing the slides, and you can see that these are the computation relations of a Lie algebra that you know probably much better than I do. So this is an infinite dimensional Lie algebra. These generators are these LMs and LNs parameterized by the integers, and there's a central element C. And for each complex number, so I'm going to look at this Lie algebra over the complex numbers, and for each complex number C, there is induced representation from one vector called the vacuum vector that gets killed by all these LNs where n is bigger or equal than -1. And just you induce a huge infinite dimensional representation of that guy. I'm going to call that guy Vir C. So it's clear from the construction that this space has a basis, a very explicit basis, parameterized by partitions. A typical vector, you write it as a linear combination of vectors of this form, where you just apply the negative modes. But since -1 kills this vector, the vacuum vector, then you should start with at least -2. So it's clear that it has such a basis of partitions where the minimal part is bigger or equal than 2. So that's a PBW basis. So let me say a couple of words here. So we have a monomial basis for this representation, and we've chosen an ordering of these monomials. So this lexicographic order gives us a total monomial order on the space Vir C. This space is graded. The Lie algebra is graded. The generator Ln has degree n, and we can declare, probably I'll use that Ln has degree -n, so that the grading is positive on Vir C. So we declare this vector here, this vector V star, this is a partition lambda of the number which is n, in this case is the sum of the parts of lambda i's. And we declare that this vector has degree n. So if we consider just the generating function, the generating sum for the dimensions of this space, namely just formally q to the n times the dimension of the space of dimension n of degree n, you get this infinite product expression for that character of that representation. So this is a very simple statement. Due to the fact that, well, this representation, we have a very explicit basis parameterized by partitions. Okay, so now something that is interesting from the representation theoretic point of view. For generic values of this, the only choice we've made was this parameter C that was a central charge. For generic values, this representation is already reducible. But for some rational values of C, namely when C has this form, 1 minus 6p minus p prime square over pp times p prime, for two co-prime numbers, two co-prime positive integer numbers, that representation is not irreducible. And there exists a unique vector that is of degree p minus 1 times p prime minus 1. This vector is what I'm denoting here, vpp prime, in that degree, and the submodule generated by that vector is maximal, so the quotient is irreducible. The quotient by the submodule generated by this vector is irreducible, and I'm going to call this the minimal model for Virasoro for that central charge, C. So that's the representation that we want to study. And there's already many things that we do not know, very basic things that we do not know about these representations, even though you either know or you might guess that these representations have been widely studied in the last 50 years. So the character of this representation of the quotient is well known. Here is written as an infinite sum again, is the graded dimensions of the generating function for the dimensions of these spaces. Here there's a symbol, forget about it. This is just an infinite product. I'm going to see it again. This is just to state that we know very well the generating function for the dimensions of these spaces. That's one thing that we know about these representations. But for example, something we do not know is what is this vector vpp prime. For arbitrary p and p prime coprimes, we do not know how to write explicitly this vector. We know it exists. We know it's in this degree. We know that so since we have a PBW filtration, right? We have a basis of the universal module VRC by partitions. We can filter by the number of parts of those partitions, and the partition of that degree with the maximal number of parts is this one, is 2, 2, 2, 2, p minus 1 times p prime minus 1 over 2 times. So what we know is that the coefficient of that partition, which is the unique partition with that many parts, is non-zero. So that's why I can normalize this vector so that I know that this monomial appears in this vector, and every other monomial that appears is going to have less parts. It's going to be deeper in the PBW filtration. But we do not know what are the coefficients of the next terms. So there's no explicit description of these singular vectors, for example. I was told once that there was, and then I was told by the same person who's in the audience that there wasn't, and I trust this person. Anyhow, so here's the questions, the very basic questions that we have about these modules. So we know that we have a basis by partitions of the universal module. So in principle, you know that some of them on the quotients they continue being linearly independent, and some of them become linear combinations of the previous ones. Since we have a total monomial order, this way you should obtain a basis, a monomial basis for this quotient, which is the interesting module, the irreducible module. What are the partitions that form a basis for this irreducible module? This is a very basic question, but we have no clue about this for the general minimal model. So I want to add one question to this list of questions. There's going to be exactly 2 questions that I want to answer in one case, which is the Ising model case. So as I said, these modules admit filtrations given by the standard for calibrated bit filtration. This is just the number of parts in your partition. The associated graded with respect to this filtration is a commutative algebra. And it's a commutative algebra which is graded, and it has a derivation of degree 1. So for example, we've seen that we have a basis by partitions for this module, VRC. And well, the associated graded is just an infinite polynomial algebra on those generators, on L-2, L-3, etc. And the derivation just sends L-n to this L-n plus 1 multiplied by n. So this is just an infinite dimensional commutative, it's non-Noetherian algebra. It's infinitely generated, but it's commutative. It has a derivation which is of degree 1. And the same for the quotient. The quotient is also canonically a commutative algebra with a derivation that is of degree 1. And it's actually a quotient of this commutative algebra. So again, our representation was the quotient of verse C by this vector. And since all the other parts, all the other coefficients in these vectors have less parts, then what we do know is that this vector should be 0 in the associated graded for the minimal model. Here, this notation is the following: is we have this infinite dimensional commutative algebra, infinitely generated commutative algebra, which is a polynomial algebra, and I'll divide by this vector here. This is L minus 2 to this power, and every derivative of that vector. So the derivative of this vector, the second derivative of this vector, and so forth. And by derivative, I mean here, this is the adjoint action of L minus 1. So there's a canonical surjection. We see that this vector is 0 in the associated graded for the minimal model. So there's a canonical surjection from this commutative algebra, which, if you know what it is, this is an arc space for the fat point, which is just the polynomial algebras in L minus 2 divided by this guy. You just take the arc space of that, or the infinite jet space of that. That's this commutative algebra, or the algebra of functions on that space. And there's a canonical surjection like this. If you take spectrums of these morphisms of commutative algebras, that's what is known as the singular support. The spectrum of this commutative algebra is the singular support of the minimal model. But here's the second question. So the first one was, give me a basis for the associated graded for the irreducible module. And the second question is, what is the kernel of that surjection? So it's a very, very basic questions that we have no clue about for the general minimal model. And I urge you to look at these questions because my guess is that it's probably possible to say something besides the trivial case or the first cases that we're doing. So here are the known results about this problem. Fagan and Frankel in 93 found explicit departitions in the case where P is equal to 2. So where you have the smallest of these two numbers is 2. It's known that the surjection is an isomorphism. Well, it's not known. It wasn't known at the time. Now it's known. It's their theorem. And they give an explicit set of partitions that parameterizes a basis for that irreducible module. And it's the partitions where the consecutive parts differ by at least, well, consecutive in, so two parts that, the ith part and the ith plus s minus 1 part. Oh, I am very stupid, and I didn't say what s is. S here is p minus 1 times p prime minus 1 over 2. And this is the this is a set of partitions that parameterizes a basis for that module. For those of you who know about partition theory, this set of partitions is a set of partitions that appear in the combinatorial version of the Gordon generalization of the Rogers-Ramanujan theorem. With Van Eckeren, we proved in 2018 that these are the only cases where this surjection is an isomorphism. So whenever P is not 2, the surjection is never an isomorphism. And I came to this problem in a tangential way. I'm interested in understanding when this surjection is, well, the kernel of this surjection is finitely generated. That's what I'm interested in. I was looking for an example where this surjection, it's either an isomorphism, or if it's not, well, is the ideal in some sense small? Is it finitely generated as a differential ideal? Okay, so here's the theorem. It's a horrible theorem. And then I'll go back to something much nicer to say. But this is our theorem. The Ising model is the first case, the first non-trivial case when P is not 2, which is P is equal to 3 and P prime is equal to 4. For those of you who know about vertex algebras, you can realize this module as this representation of Virasoro as the even part of the free fermion vertex algebra. So if you just take an infinite Fock space for the Clifford algebra, and you look at the even space at central charge is equal to 1/2, which is C for this combination of numbers, you're going to find this this Ising model. And you know, or you can guess that this is very well known, this Ising model. For example, I just told you that it's representation of the Clifford algebra, so you have an explicit basis as by modes of the Clifford algebra. So what we prove is that the surjection from this commutative algebra to that graded, the kernel is generated by only one element, and is precisely this element. So this element is 0 in the quotient, and every derivative of that element is going to be 0, and nothing else is 0. So that's the main theorem. And the specific basis, I guess that's why this is something typical from trying to find specific monomial bases that come from representation theory. The partitions that appear are horrible. So the partitions that parameterize this irreducible modules are all partitions that do not contain this sequence of subpartitions. So this is not, I understand this is very ugly, but this is what it is. You cannot do better than this. So for example, this first line says that the same part cannot appear 3 times. Actually, if you read these 3 guys here, it says that if you look at one part and the next one and the next one, then the difference between these 2 should be at least 2, which is something that appears in the Gordon's, Rogers, Ramanujan condition. Actually, these 3 conditions are the same that for Frenkel's condition for p is equal to 2, but for p is equal to 3. But well, but there are some more conditions. So all of these things are infinite families of subpartitions that shouldn't appear, some monomials that shouldn't appear. And these 4 guys are exceptional. So these 4 guys should not appear in these partitions, and that's it. That's what it is. So I'll tell you how to prove this theorem. The proof is very simple, but I want to tell you some consequences of this theorem that I think is more important. So the generating function, so that this is the main consequence, I would say, and is that the character of this Ising model that is very well known has this explicit double sum expression. So this is a double sum of q to a quadratic form divided by 2 q numbers. I'll define this number soon. Multiplied by, it's just a linear combination. So the fact that the character of the Virasoro module can be written in this form, I think has some deep consequences. Okay, so now I'll just rush through. So this was just the 4 slides to tell you what our theorem is. So now I'll just go to slowly get to how to prove that theorem, or how to guess that that theorem should be true. So partitions appeared everywhere. And so now I'll just take it very, very slowly for people that there's many students in the audience, I guess. The number of partitions of n is the way of writing n as a sum of positive integers. We order those integers in a non-decreasing way. And here's the number of partitions of 5, which is 7. And these are the 7 ways of writing 5 as a sum of other positive integer numbers. So counting partitions has been something that we've been interested in since ever in mathematics. Euler has this theorem saying that the number of partitions of n into an odd part is equal to the number of partitions of n into distinct parts. Rogers and Ramanujan is essentially the first highly non-trivial idea after Euler. There were some bijective proofs of new ideas after Euler, but this is really something new. The number of partitions such that 2 consecutive parts differ at least by 2 is equal to the number of partitions of n in parts that are congruent to plus or minus 1 modulo 5. This is a theorem that took 200 years since Euler's theorem. Jackson proved in 1928 in a disguised form. It was only known after Slater's proof in 1955. Different version, that is the number of partitions of 2n into distinct odd parts is equal to the number of partitions of n into parts that are congruent to, well, this congruence is modulo 16. And this theorem is the one that is going to be relevant for the Ising model, the last theorem. That's why I'm citing it. So I probably should rush through this slide, but this was just to just take a proof. So this is a typical situation for these Q identities that we're going to try to prove. You have an infinite sum that you can express as an infinite product. So here Pn is the number of forms of partitioning n, and I claim that the sum of Pn times Q to the n is this infinite product here. And the proof is very simple. You just take this rational function that you view it as this series given by the geometric series, and just take this infinite product. So that's the infinite product. It's just the product of infinite product of series. So now the coefficient of Q to the n, well, it's clearly when you need to pick one summand from here, one summand from this one summand from the other one. So this is an infinite sum where parameterized by these guys. You just have K1, K2, K3. K1 means you chose the K1 summand from the first one, the K2 summand from the second one, and so forth. So all of these summands, they all have to be either the first one, all of these factors should be 1, except a finite number of them. And that's clearly the number of partitions of n. All right. So those are the kinds of identities that I'm going to be interested in. They are all of the form an infinite sum equals an infinite product. This is a theorem of Euler. This denominator here is what I'm going to call, this is what appeared before as Qn, the quantum number, the nth quantum number for Q, or Bochhammer symbol. This is a theorem of Jacobi that, you know, it's important because, well, at that time, I mean, this is some elliptic function, and this is Jacobi theta function. And what Jacobi proves is that this series here, it can be expressed as this infinite product. So now, if you know that this series converges, and this series converges very fast because it's Q to the n squared. So if you put Q to be e to the 2 pi I tau, this converges in the upper half plane very, very fast. So you can actually do computations with this series. With just knowing a few summands, you can actually do computations with arbitrary precision. And they did this at the beginning of the 1800s. But on the other hand, you know that this function here is an infinite product. So if you know that it converges, and it converges on a holomorphic function, you know where the singularities are, and you know where the zeros are of this function. This is a similar theorem. Oh, I'm sorry, I'm moving my mouse. This is a similar theorem by Gauss that, again, looks like an infinite sum of Q to some quadratic power of n. This Jacobi condition is also Q to some quadratic power of n. Notice that Euler's theorem is Q to some linear power of n. More of these identities, again, an infinite sum equals an infinite product. So it's easy to see, it's immediate to see that this infinite product here parameterizes partitions with certain, partitions of n where with parts that are congruent to either 1 or 4 modulo 5. The proof is the same as the one that we did for Euler's theorem. So that's one side of the Rogers-Ramanujan's theorem, counting two sides of partitions. It's not so trivial, but it's not hard to see that this side here parameterizes the other set of partitions for the Rogers-Ramanujan one, where the two consecutive parts have difference at least 2. And here's the Jackson-Slater again. This side here is immediate, that this parameterizes partitions with this congruence with parts, with this congruence is modulo 16. And on the other side, this parameterizes partitions of 2n in distinct odd parts. That's also not hard to see. And this is the theorem that is relevant for us. Again, this theorem is relevant for us because these sides, both sides, are the character of the Ising model. Okay, so all the generating functions that appeared, the order of these infinite sums that appear, are, well, form a power series with positive integer coefficient. That's clear. That's just by definition. They are counting partitions. But they also converge. They converge absolutely and uniformly in the upper half plane whenever you put Q is equal to e to the 2 pi I tau. And they are all invariant, in some way invariant. They're either modular forms or they're a component of a vector-valued modular form. But they all have nice properties with respect to the modular group. And, well, that's no coincidence. I'm going to make a comment about this in a second. So let's get back to representation theory. The character of the Ising model, this here, this infinite product, this expression, the character is this fourth line is an expression that I already have given in general for all minimal models. Pagan and Fuchs have a computation of the character of this minimal model that goes along this line. It's an infinite sum divided by this infinite product. And this is a special case for the case of the Ising model, which is the Virasoro 3-4. These are all different kinds of expressions for the same character, for the same sum. This first line here is essentially the fact that you have a basis by the even part of the free fermions. The second line is, this is the theorem of Jackson and Slater. This is just another way of writing those congruences modulo 16. The one that is very surprising that appears here is this last sum. This last sum is very surprising. The Cartan matrix for E8 appears in this sum. All of these sums are sums on one parameter. This is an infinite product, but this is also a sum with one parameter over C. This is a sum with 8 parameters. This appeared in the early 90s as a conjecture of Kedim and a series of physicists in Stony Brook. It was proven a couple of years later by Barnard, and I don't remember the collaborator. It's actually, to this day, I don't understand that proof. It's something about the Bethe ansatz. They prove a polynomial version of this identity, that this sum here equals this other sum, and then they take a limit, but then it's not clear to me how the proof of that polynomial version goes. Anyhow, it's a very surprising result. So let's get back to our theorem. Our theorem is that all of those expressions that we had before have another one. You can add one to that list, that is this double sum. This double sum. And this double sum has lots of things in common with the sum for the Cartan matrix of E8. These are called num-sums, where you have Q to some quadratic expression. Here's just a positive symmetric matrix A. So you have Q to some quadratic expression in your parameters, K. In our case, K is 2 parameters, it's in Z2. In the case of the Cartan matrix of E8, K is a parameter in Z8. Actually, this in the Cartan matrix of E8 case, this is really just the inverse is the Gram matrix for the weight lattice of E8, right? So with the standard inner product. So you have Q to some quadratic power of your parameter K, and you divide by quantum numbers, QK1 up to QKn. So that's a sum like this is called a num-sum. And in our case, this sum here, if you forget about this parenthesis here, this sum here is a num-sum for this matrix. A is A332. And it has an interesting history. So it's a linear combination because you can absorb. These parentheses are linear in the parameter K. So this is a sum of 3 such num-sums. So let me tell you something about this, why they're called num-sums. Werner Nam has a conjecture. It's a very deep conjecture relating K theory with number theory, with modular forms. And it's conditions on when this sum can be modular, can be somehow invariant by the modular group. And they in particular give, by just studying the asymptotics, they give conditions on this matrix. What are the possible matrices A such that there might exist B and C where this sum becomes modular? And the conjecture is that the possible matrices like this have something to do with torsion elements in the K2 group, in the block group. We're not going to get there. We don't really care about this. But the whole point is that this was very much studied both by number theorists and K theorists. And in particular, for matrices of rank, well, for rank 1, this is very well known. This is a simple case. But for rank 2, for matrices of rank 2, a student of NAM, Terhoeven, and then Don Zagier ran with computers a huge parameter space, and they found infinite families of matrices of rank 2 that satisfy those conditions, where this sum becomes modular, and a few exceptional cases that have the right asymptotics, and they couldn't find any B or C such that this sum becomes modular. And this matrix here, A332, is one of those examples, one of those exceptional examples where there's no modular sum. So our theorem is saying that, well, one sum might not be modular, but if you take linear combinations of NAM sums for that matrix, actually becomes modular. Because the characters of Virasoro, they are nice with respect to the modular group. There's 3 representations. They form a 3-dimensional vector-valued modular form. Well, the 3 reducible representations for the Virasoro at that central charge. So this is one of them. Actually, our theorem produces 3 such identities for each one of the characters of the Virasoro LieJor at central charge 1/2. We have other sums. They are all for the same matrix. The only thing that changes is this linear combination here. The proof of that identity, so I want to prove this identity, right? I want to prove that one of the sums is equal to this. And the proof of this identity is completely elementary once you have the right idea. This is not my idea. This is the reason why George Andrews is one of our collaborators. Actually, I posted this in Math Overflow as a conjecture that I couldn't solve. I had tested it in computers to a very high degree. I'll tell you later how we got to that conjecture. And I didn't know how to prove. I tried this technique of finding polynomials that in some limit actually to arrive to our series, but I couldn't find them. And it took George Andrews just a couple of weeks to conjecture these polynomials. So you just have 2 families of polynomials. These are quantum binomial coefficients. As you take n goes to infinity, this Sn, it's immediate that it goes to this sum. And it's not so immediate, but well, it's very simple to see that as n goes to infinity, Tn goes to our sum, the sum that we wanted to take that it was equal. So we want to check that these 2 things are equal. And it just so happens that for each n, these 2 polynomials are equal. So how do you check this? In principle, you may be able to do this by hand. I do not know how to do this yet. We put this in a computer. We use the computer package for Mathematica that finds the same recursive equation. And it's an equation of order 15 for both of these polynomials. And then you just check that both of these polynomials have the same initial conditions that you can do by hand. And they satisfy the same recursive equation for n. So it's a very elementary proof. The genius here is to guess these 2 families of polynomials that I'm guessing that it has to do with like the many years that our collaborator has working on these kind of problems. Okay, so this is the theorem. This is the ugly theorem, and I want to tell you how one arrives to that. So I have a few minutes. I want to tell you how one arrives and what's my interest in these kind of problems to this theorem. So I'll give you the proof of the rest of the theorem. That it's actually completely independent of this identity here, that is here. So the first thing we'll prove is that the generating function for the partitions, these partitions Pn, that do not have these partitions here, is this sum on the right. And what you do is you subdivide your partitions into subsets. And these subsets are very simple. Let's go back. I'll go back one slide again. And now we look at the horrible set of partitions that we are not allowing. Notice that there's the singularity here, and the reason why these 4 exceptional cases appear is because of this p bigger or equal than 3 here in this line. Namely, 5, 3, 3 is not allowed. the partition when p is equal to 3, this is 5, 3, 3. That subpartition is not allowed to appear in a partition in Pn. But 4, 2, 2 is, because this starts at p is equal to 3. All the other sets, they start at p is equal to 2, which is the minimal part, and whenever you add 1 to each one of the parts, this partition is still not allowed. But this one is very special. It starts at 5, 3, 3, and it doesn't start at 4, 2, 2. 4, 2, 2 is allowed. So all these exceptional cases end in 4, 2, 2. So the division in 5 subsets is going to be according to how many 2's do you have in your partitions. You know that you cannot have 3 2's because 2, 2, 2 is not allowed by this. So you can have either no part 2, 1, 2, or 2 2's. And our subsets are: A is when no part 2 appears. B is when 1, 2 appears, but 3 does not appear. C is when, well, 2 appears and 3 appears. D is when you have 2 2's. And now you have 2 and 2, and the next one is not 4. And E is when you have 2 and 2, and the next one is 4. So those are the 5 subsets that you divide, and you find an explicit recursion between these sets. This recursive system is very simple to describe, given this decoupling. So, for example, here I'm saying that the partitions that don't have a part 2 and have m parts, you can describe them in terms of these partitions here. You can see that you see A, B, C, and D. The only one that doesn't appear is E, and E is the partition that contains 4, 2, 2. And why is this? Because if you add 1 to the partition 4, 2, 2, you obtain 5, 3, 3, which is not allowed. Actually, the only partition that when you add 1 to each part, it becomes not allowed is 4, 2, 2. This was because the only one that started at p is equal to 3 was 5, 3, 3. So this identity here, the first identity, means that if you grab any one of these 4 first terms and you add 1 to each part, then you have one allowed partition in the first one, in A, because now that partition will not have a part 2, because you added 1 to all of them, and the minimal part was 2, so now you don't have any single 2. So that's this identity here, that map is bijective. And all the other ones are more or less the same thing. So now that you have a recursive system, you can guess the answer. And that's what we did. That was very simple. This guessing didn't really take much, probably 1 month of trying, but I'm sure that someone that was experiencing this kind of identities would have guessed it in 1 day. So these are the generating functions for the 5 subsets of partitions. And you just check that these functions satisfy that recursive condition, those recursive equations. So it's very elementary. As a high school student could check this. Again, it's just guessing the answer to the problem. So now we know that the generating functions for our partitions are these guys. And we want to prove this, that this quotient is the associative gradient. And again, this is this is an exercise on vertex algebras or representations of the Virasoro Lie algebra. This is the vector. I'll go 1 slide more. This W34 is this vector. This vector here that we want to prove that it's in the kernel. So this is our vector, and we notice that this vector is in the 3rd degree of the filtration, the PBW filtration. These are partitions with 3 parts. And the Ising model is a quotient by this vector that is very explicit. That is also, the leading term has 3 parts. It's L minus 2 cubed. This guy has only 2 parts, this guy has 1 part, and this guy has 2 parts. But by direct computation, you just compute that this vector here, you can subtract. These are modes of the Virasoro model applied to the V34 that is in the kernel, and you get this combination here, but this combination is deeper in the PBW filtration. There's a discrepancy here with the 3 and the 5. This I should have written here 2 instead of 5. with the names that I'm doing. So 3 here means something different than the number of parts. But anyways, for the number of parts, it also works. This is three parts, and this side here has only 2 parts. So that's why this vector here, modulo v34, becomes 0 in the associated gradient. So that's why we have a surjection from our quotient algebra by this vector into here. But we have a surjection, so now we have this commutative algebra being a quotient of this other commutative algebra. We know the character of this commutative algebra. This is the character of the Ising model. And all that we need to know now is therefore find a basis for the ideal generated by these guys. And what we do is we just prove that each one of these partitions, this horrible set of partitions that I wrote, is the leading monomial for some Grobner basis. Well, is the leading monomial of some basis of this ideal. So actually, we came to this theorem this way. What we did is we knew that this vector was in the kernel. We wanted to prove that this was the unique vector in the kernel. So we put in a computer and asked, can you give me a Grobner basis for this, for the ideal generated by this vector? So the computer came and it gave us this set, except these exceptional guys. We put it up to degree like 14. And we spent months trying to prove that this set, without these exceptional guys, was going to be the right answer. And we couldn't prove it. We started to suspect that it was false. Then we let the computer run for longer. You see this monomial here has degree 31, I think. And that took a few hours in my laptop to compute. It took like 18 hours in my laptop to get to this guy. So we were very disappointed. We didn't know if more of these exceptional cases would continue to appear in higher degrees. And it turns out that it doesn't. So for me, this is kind of a miracle. We asked for a Grobner basis. These were the leading monomials of those Grobner bases. This is a typical problem in this kind of problems, that you ask for a Grobner basis and the partitions that appear, the monomials that appear, are horrible when they come from representation theory. But anyway, so this is one instance where you can actually solve this problem and compute count those partitions given by those Grobner bases. So the summary of what we have is that we found an explicit monomial basis for PBW basis for the Ising model. This is the very first non-trivial representation of Virasoro. We found new Q-series identities that are of the Rogers-Ramanujan side. The fermionic side means here the sum side. The product side stays the same, but the sum side typically has different weights. And this is a combination of num sums. And we proved that the kernel of that surjection is generated by the single element and all of its derivatives. So now, more generally, I guess I'll just say a few words for those of you who know about vertex algebras. Whenever you have a vertex algebra, it has 2 associated commutative graded differential algebras. One is taking its associated graded. That's the classical limit of this vertex algebra. This is the analog of this algebra A34 that I have. And the other one is to take the arc space of the C2 quotient. Now, the arc space of the C2 quotient, I'm sorry, it's exactly the way they were. The arc space of the C2 quotient is always larger, and the associated gradient is smaller. So there's always a surjection. And the question is when this surjection is an isomorphism. This holds for any vertex algebra you have this question. And up to our theorem with Van Ekeren in 2018, it wasn't even known if there was an example where these weren't isomorphic. So we've shown that most minimal models, when P is not 2, they are not isomorphic. But now the next question is, when is it, if they're not isomorphic, when is the ideal finitely generated? And this Ising model provides the first example where it's finitely generated. We know it's finitely generated by one guy. So now if the next example for Virasoro would be the tricritical Ising model, that's P is equal to, so that's 3,5. I'm sorry, 4,5. It's also the unitary guy. So I have a computer at IMPA with 192 cores computing that Grobner basis. and I've had it for over a month now, and it still hasn't converged. And I know that there are generators in the kernel for that ideal up to degree 41. There's at least 6 generators for that quotient, and I have no hope of computing the next one. This grows dramatically hard. So when I started this project, I thought that this would be easy to do, obtaining Q-series identities analogous to ours for other modules for Virasoro. But now I took the next step, and I couldn't get anywhere. So probably we need a new idea to do this kind of problems. Anyhow, so I just wanted to say that there's something very basic, a monomial basis for the Ising model that I'm very surprised that this wasn't known. But okay, here it is, and it's horrible. And hopefully this same problem can be applied for, say, affine algebras. We know it for SL2 at integer level, we know this. For SL3 at integer level, I think we know it. For SLN at integer level, I've seen claims, but I haven't seen the actual proof. Anyhow, so I'll just stop right here.
Okay. Let's thanks Reimundo for talk. Any questions, comments?
One small question. In slide 13 or 12, you have summation.
Slide 12, let me just go there. This one, yeah.
13, I don't remember. And you 13, have summation from n is starting from 0. Because if n equal to 0, you have...
Yeah, no, I'm sorry. Here, yeah, so sure. This is n is bigger or equal than 1, yes.
Bigger than 1, so you probably you can interpret this like empty product, and so the first term will be equal to 1.
Yeah, so here is 1 plus, yeah, I wrote this wrong. In both of these guys, you have to write 1 plus the sum for n bigger or equal than 1.
Okay, thank you.
Okay, more questions? No questions, comments?
Oops.
Okay, if there are no more any questions, comments, let us thanks again, Reimundo, for very well. Thank you, Reimundo.
Thank you.
And just I want to announce that the next Thursday we will have a talk by Professor Leonid Makar-Limanov from Wayne University, United States. Okay, so thanks everybody for participation, and till the next Thursday. Bye-bye.
Thank you. Bye-bye.